Welcome back, and I do hope as ever you and your family are keeping well. So what we're going to look at in this lesson is wave intensity. We're going to look at how the waves that come off a point source spread out and how their energy gets more and more spread out with increasing distance. So let's look at wave intensity and what it means. So the first thing we need to know is that we tend to abbreviate the word intensity to the letter I. And I will be measured in watts per metre squared. I'll put in there so you can see, separate the abbreviation of intensity that we use in formulae to the unit that we use, SI unit. Okay, so if you think about it, it's the power delivered to a metre squared. I'm not going to do the calculation for my projector, but if you look at this screen, shall we say that it's 4 metres squared? Okay, so if I've got 400 joules per second hitting it, 400 watts, then I've got 100 joules per second on every metre squared, 100 watts per metre squared. So what would happen if I pushed the screen back? Okay, well, the energy hitting it wouldn't change. Yeah, the amount of energy hitting it per second, the power wouldn't change, but the intensity would, because this image would get bigger and bigger and bigger. In other words, the number of joules per metre squared would go down. Now, you and I would interpret that or see that as the image getting dimmer. So you've got an idea now that the intensity of a wave is caused by the wave energy coming from a point source. So imagine something like the sun at a distance, or a star, or a light bulb, throwing its energy out in all directions. It spreads out as we back off from the source. Okay. In other words, the amount of energy per second, the power on every metre squared of surface area, gets less as we move further away from the source. Now, I've stretched my drawing skills to the limit here, and I've drawn a point source here. So imagine that's maybe a light bulb giving out light in all directions, okay, in sort of a spherical shape, okay, and or you can imagine it's the sun or a star. And I'm going to back off from that a distance r. So I've moved away a distance r. And then what I'm going to do is double that distance away from the source. So I'm now going to move away 2r. Okay. You might wonder where this r comes from. You're going to get very familiar with that later on. If you can imagine the light coming off this in sort of spheres, okay, this surface will be slightly curved and this surface will be curved. But the point I'm making is that really it's a radius of a sphere of surface that the energy is spread out upon. Okay. Now, again, my drawing skills tested to the limit here. But if we back off a distance r, we've got a surface area here. Okay, so here's our surface. Now, I did say that for bigger distances, this is a sphere, so this will be slightly curved. But let's just draw it as a sort of window. Now, if we back off to twice the distance, the important thing you understand is these lines have separated by twice and separated by 2 times this way as well. Okay, so if this base length here is twice as long and this height here is twice as long, then if we double the distance away from the source, we've actually 4 times the surface area. So each one of these, not very clear from my diagram, but each one of these will be the same area as that piece. So what's happened to the intensity? Well, we've got an intensity here of I, but you notice that if we've doubled the distance away from the source, the intensity goes down by 4 times. And remember that this intensity is the amount of joules per second hitting each metre squared of surface area. Okay, I've got another way of showing you this. So imagine a point source of waves here in the middle of this little sphere. Okay, and we'll give the radius of the sphere as r. So this distance across here is r. And then what we're going to do is we're going to back off to 2r. So this really should be twice the radius from that point. So if I label that r, I hope you can see that the whole of this thing from the midpoint from here to here is twice the radius of the smaller one. Okay, so we've got r here, r there, so the bigger sphere has a radius of 2r. Now, if you remember, intensity is about how the energy spreads out onto this surface as we back off, because we might be standing here, if you see what I mean, looking that way, or we might be standing here, preferably with a metre squared screen to work out the amount of joules per second hitting that 1 metre squared. But what you need to know to work this out is that the surface area of a sphere, the surface area, is equal to 4 pi r squared. And it's that r squared that's so important when we do this work, because if we look at the area of the little sphere, so we look at this one, this has an area of a, shall we say? Okay. But remember that area scales with radius squared. So if we double the radius, 2 squared is 4, so this surface here will have 4 times the area, okay? And if you think about that, if it's got 4 times the area, then the energy that this is giving out is now spreading out on 4 times the area, so the amount of energy hitting every metre squared is 1/4, so the intensity at twice the distance from something is 1/4 the number of watts per metre squared. So let's look at this a little bit further. There's something really interesting that we can do if we understand power and intensity. If you have an object where you know its power, okay, and you back off from it, or you're a distance away from it, but you don't know what that distance is, and I'll come back to that in a minute, but you will know, of course, the intensity of the energy, the waves you're receiving where you are, you can actually calculate backwards to the distance to that point source. Now you might say, why do you need to do that? Okay. Well, there are some very interesting cases, obviously backing off from light bulbs and things we've discussed with my projector. But what about stars, or particularly supernovae explosions? There are some supernovae explosions where the power is actually known reasonably well. They're sort of similar stars. Okay, so you get a supernova explosion that you kind of recognize from a previous star that was similar doing the same thing. So you might actually know the power of that supernova explosion. Okay, so you're looking from Earth using a telescope or what have you, and you can measure the intensity of that energy that comes from the supernova explosion, and then, because the intensity is massively reduced, you can then calculate how far away that supernova explosion was and get some idea of the distance to that very, very distant star. So what we're going to do now is look at how we can do that mathematically. So let's look in a little bit more detail about progressive wave intensity. So I'm going to give you a definition, but firstly let's remind ourselves what a progressive wave is. Okay, this is easy. It's just a wave that's traveling through space. Later on we're going to look at standing waves, and they're more complex, but all the physics I'm doing here is about something giving out waves, sound waves, light waves, etc., from a point. So imagine the sun radiating light or radiating heat. Okay, so let's have a definition, and remember that definitions do not have units in them. Okay, it's just kind of words. If you remember, it allows you to use any units you like. So we're going to define the progressive wave intensity as the power passing through a surface per unit area. Okay, so I haven't used any units there because we could be working in inches squared or feet squared or what have you. But of course, in SI units, it's the number of joules per second passing through every metre squared of surface area where we're making our measurement. So, in other words, we can write that down as a formula. I, the intensity, is the power passing through each unit area. Okay. Now, we've been looking at point sources. So, for a point source, it's a specific case. Because obviously you can have intensity of a laser beam at different distances, but the maths we're doing here won't work that out because we're not imagining the beam spreading out over a sphere. So for a point source, we've got I equals P over A, but we know that with a point source, the energy is spreading out over a sphere. So if I draw a sphere here, there it is, okay, and there's its diameter. Then this distance here will be its radius. And if you think about it, from the point source to this surface, we've got some energy per second coming from that point, spreading out over a surface area. But because it's a sphere, we know that surface area. Okay, we know that A here is 4 pi r squared. So we can rewrite this formula for a point source, yes, a special case. The intensity will be equal to the power divided by the area, which is 4 pi r squared. And we're going to use that formula quite a lot. Just get your head around what it all means. Okay, this is us at this distance r. Okay, and that's the power of the source. So in some ways, you could imagine the intensity reducing, yeah, as we increase the distance from the source. Okay, as r gets bigger and bigger, r squared will get much bigger, and the power of the source is divided by r squared. So as we back off, the intensity where we are on this surface reduces. So what I thought we'd do is a little calculation, and this is quite a fun and very typical one. Let's see if we can work out the power of the sun, the number of joules per second given out by the sun. Okay, well, we need some numbers to do that, and there's a few things that we know. Okay, every solar panel engineer worth their salt knows that number. They know that on a good day during the day, we get approximately 1.4 kilowatts of energy per metre squared hitting the Earth's surface. Obviously, it varies, but we'll work with that number. And most physicists know the distance between the Sun and the Earth. Again, it varies slightly, 150 megakilometres, so we'll a little bit closer, 148 million kilometres. And what we're going to do is we're going to use those numbers to work out what the sun's power is. So if you remember, intensity was the power per cross-sectional area. Okay. And if we want to work out what the power is, okay, of the sun, then we need this P. Power is equal to intensity multiplied by area. Now, the area we're going to use is the area of the sphere that touches the Earth's surface. Remember that the light has been spreading out and spreading out and spreading out over an ever bigger sphere, and it has a radius, that sphere if you imagine, of the distance between the Sun and the Earth. So we know that this A is 4 pi r squared. So let's put some numbers into this now. Right, so the power of the Sun. Now, it's a sort of common physics thing to, instead of writing the word sun, just to put a circle and a little dot. It's a sort of ancient symbol for the sun. Okay, well, here we go. What will the power be? Well, it will be the intensity where we are, 1400. Now, we're in the right units, so be careful for kilowatts per metre squared, multiplied by the area. And again, be careful with the units here. So it's, I'll put it all in brackets just to show you. It's 4 pi, you don't need to, 4 pi r squared. And our r is 148 times 10 to the 9. And then it's that one squared. Okay. Obviously, you don't need the brackets here, but I'm trying to show you the two different terms. That's the 4 pi r squared term. Okay, so we get a calculator, and the power of the Sun is equal to about 3.9, so two significant figures, times 10 to the 26 joules per second. Okay, an absolutely phenomenal power. Now, this is assuming it's a point source, of course, but that's pretty much about right, actually. That's what we'd expect on the surface of the Sun. So it's actually the radiated energy per second. So finally with this, just a few little things to note. I think you know this already, but I want to make it clear. And if your math skills are good, then you don't really need this. But it's that point about what happens as we increase R, as we increase the distance. So we know that the intensity is equal to the power per surface area. Okay, so the intensity is proportional to 1 over area. And we know that intensity, therefore, is proportional to 1 over, well, there's a 4 pi in there, but over r squared. So what that means, of course, is that, sort of therefore, if we go to 2r, twice the distance, yeah, we need to do here, look at our intensity, 1 over 2 squared of the intensity. Yeah, in other words, a quarter of the intensity by doubling the distance. And we started off with that sort of at the beginning of this lesson. But think about what that means, for example, if we go to 100 times the distance from an object. So we're at a distance, and then we increase that distance 100 times. Okay, therefore we will get 1 over 100 squared of the intensity. So that will give us an intensity, yep, that is 1 over 10,000 times less. Okay, so I'm just making the point here that you need to be aware that because it's an area, the intensity is scaling with 1 over r squared. So let's now look at how intensity and the amplitude of the wave interrelate. So a really easy example to do is waves on a pond, ripples on a pond. So we're looking down here at something at the center there that's bouncing up and down and releasing energy out in these circular ripples. And the bit you need to be aware of is, and we'll keep it simple, is that the energy this is producing here is spread out over this circle. And then if there are no losses, it's now spread out over a bigger circle. So there's less energy per piece of circle, as it were. So the wave amplitude must drop. Now this is working nicely here for water waves, and it works nicely for sound. It's a little bit more complicated with electromagnetic waves, so we'll kind of come back to them later. But there is a connection still between intensity and amplitude with electromagnetic waves, but it's not quite the same thing because we're dealing with photons. So how can I show you the wave amplitude reducing here? That diagram doesn't show it. Well, pop your head up out of the water and see the waves go past. So I'm going to draw a little construction here to help me with this. Okay, you'll see what I'm doing in a second. I'm going to draw myself a little sort of trumpet shape here. Right, now that'll help me draw what I want to draw. So if you think about it, here you're going to see a peak. Here you're going to see a peak. Here you're going to see a peak. And there you're going to see a peak. So how do I draw that? Well, here's a peak. Then there's a trough. Then the next peak. Then a trough. Then the next peak. Then a trough. And finally to the middle. Oh, I haven't done too badly there. Okay. So we've got a high amplitude at the midpoint, and then a lower and a lower and a lower as that energy spreads out over the rings. Okay. So you'll notice, of course, here that as R goes up, so in this case we're moving to the left. So there's our 0 point. And we're increasing our separation from the source. As R goes up, the amplitude of the waves goes down. And so what I want to do is I want to show how that affects the intensity at any point along R. So let's see if we can work out how the intensity of the wave relates to its amplitude. And intensity is not the same as amplitude. Okay, so I've said clearly a lower amplitude means that the particles have a lower vibrating speed on average. Okay, so a particle at centre is having to move through a very large distance to create one single oscillation, and a particle here is moving through a smaller distance in the same amount of time, so it has a lower average speed. So imagine what happens if we have twice the amplitude. Okay, well, what I'm suggesting is that if we have twice the amplitude, on average, the particles are going to have to move twice as fast to cover that ground in the same amount of time. Okay, so if we double amplitude, we double the speed of the particles. But intensity, relates to energy. Now, these particles have got kinetic energy. So kinetic energy, if I can write it E sub k, is equal to a half m, and here's the important bit, v squared. Okay, so if we increase v, so 2 times v, that's going to give us 4 times the kinetic energy, because the kinetic energy scales with the velocity squared. So double the amplitude, you're doubling the velocity. Yeah, double the amplitude, double the velocity, 4 times the kinetic energy. So what we notice here, therefore, is that the intensity, which relates to energy, is proportional to the velocity squared, or more correctly, should we say, the amplitude squared. And that's a really important result in physics, in fact, and it plays a very interesting part too with electromagnetic waves, and it plays a really interesting part. You'll come across this again maybe much later on when you do some quantum mechanics. This idea that the amplitude, it becomes a probability amplitude with quantum physics. If you square the amplitude, you get some idea of the intensity. Okay, now we don't really need to do the quantum stuff, but for mechanical waves, we know this to be true. So I do hope you found that lesson useful and you feel you've got a good understanding of what is meant by intensity now and how to use the intensity formula to calculate either intensities, powers or distances away from an object that's radiating waves. Anyway, I'll be making another video soon and I look forward to seeing you then.